Hey everyone, welcome to This Explainer. Today, we're popping the hood on Earth's climate. We hear about it literally all the time, right? But how often do we actually look at the structural framework scientists use to define it, or the fascinating mechanics of how and why it changes over time?
Let's just jump right in. 14 degrees Celsius, that's our anchor. It's the incredibly delicate baseline of Earth's annual average near-surface air temperature. Keep this 14-degree number in the back of your mind today, because every single mechanism we're going to talk about is ultimately pushing or pulling on this one global thermometer.
All right, here's our game plan for today. Mapping Earth's climates, natural climate change triggers, the greenhouse effect explained, ozone depletion and CFCs, and finally, global impacts and action. Let's get to it. Section 1. Mapping Earth's climates. So, let's start with the status quo. How do scientists actually organize the sheer, dizzying chaos of our planet's weather patterns into something we can study? Well, the answer is the Köppen scheme. Developed way back in 1918 by Koeppen, it's this empirical classification scheme that is still incredibly popular today. Koeppen basically realized, hey, there's a super tight relationship between vegetation and climate. So he built this sort of secret code based on monthly temperature and precipitation. Notice the major groups here. Capital letters A, C, D, and E represent humid climates, while B stands for dry climates. Then we just tack off in small letters, like F for no dry season or S for a summer dry season, to nail down the exact seasonal vibe.
Let's decode one of these, all right? Take AF. That stands for tropical wet climate. You're going to find this hanging out right near the equator. Think the Amazon basin or the East Indies. The characteristics: you're getting significant thunder showers every single month, usually in the afternoon. And the temperature is just incredibly stable, hovering right around 20 to 30 degrees Celsius, with almost zero annual range. Because of that rock-solid stability, this climate supports massive, dense, evergreen canopies and just unbelievable biodiversity.
Or what about seas? That is your classic Mediterranean climate. You're going to find this along the west coast of continents in subtropical latitudes, so between 30 and 40 degrees. We're talking Central California, Central Chile, parts of Australia. But the mechanics here are totally different. In the summer, subtropical highs roll in and give us hot, dry conditions around 25 degrees Celsius, literally perfect beach weather. But then winter hits, westerly winds take over, and bring mild, rainy weather that dips below 10 degrees. It's just a fantastic example of atmospheric forces shaping a highly specific regional environment.
Moving on to Section 2, Natural Climate Change Triggers.
Now that we've got our baseline map, we have to look at the massive natural forces that can completely disrupt those established zones. And this is a crucial point. Climate change isn't purely a modern, human-made phenomenon. It has deep historical roots driven by two main categories: astronomical and terrestrial. On the astronomical side, you've got sunspots, these dark, cooler patches on the sun that cycle up and down. Some meteorologists actually link high sunspot activity to cooler, wetter, stormier weather here on Earth, and fewer sunspots to warmer, drier days. On the terrestrial side, volcanism is a massive player. I mean, when Mount Tambora erupted back in 1815, it threw so much ash into the sky that 1816 became known globally as the year without a summer. Another absolutely wild astronomical trigger is something called Milankovitch oscillations. This isn't about the sun itself changing, but rather Earth's physical relationship to it. Over these massive, agonizingly slow cycles, Earth's orbit around the sun actually changes shape, the planet itself physically wobbles, and its axial tilt shifts. All of this planetary gymnastics fundamentally alters our solar insolation, basically how much incoming solar radiation we get, which heavily impacts the global climate.
Which brings us to Section 3, the greenhouse effect explained. To really grasp the most significant modern shift, the human-caused effect on our climate, we have to talk thermodynamics. Let's define the greenhouse effect directly. Our atmosphere is actually great at transmitting incoming shortwave solar radiation straight down to the ground. But when the Earth's surface warms up and emits that energy back out as long-wave radiation, the atmosphere absorbs the vast majority of it. The specific gases doing that absorbing, those are our greenhouse gases.
Let's break down how this warming builds step by step. Step 1. Sunlight. Coming in as shortwave radiation, passes through the atmosphere like it's barely even there. Step 2. The Earth absorbs that light, warms up, and radiates the heat back up as long-wave radiation. Step 3. Instead of just escaping into the void of space, this long-wave radiation smacks into greenhouse gases. They absorb it, trap the heat, and basically turn our atmosphere into a giant thermal blanket.
So who are the culprits here? The primary greenhouse gases we're concerned with today are carbon dioxide, chlorofluorocarbons or CFCs, methane, nitrous oxide, and ozone. Carbon dioxide is the heavy hitter here in terms of concentration, mainly pumped out from burning fossil fuels like oil, gas, and coal. And we're seeing its concentration rise at about 0.5% every single year. We also have to keep an eye on things like nitric oxide and carbon monoxide because they easily react with these primary gases and mess with their concentrations even more.
Now here's the kicker. Not all greenhouse gases are playing the exact same game. A molecule's actual warming power depends on three things: how fast its concentration is spiking, the specific wavelengths of radiation it absorbs, and crucially, its lifetime in the atmosphere. For example, carbon dioxide relies on natural sinks like forests and oceans to get absorbed, but because of deforestation, we're losing those sinks fast. It actually takes 20 to 50 years just for atmospheric CO2 to adjust to changes in these sources and sinks. Basically, the longer a gas hangs out up there, the longer it takes for Earth to recover.
All right, Section 4, Ozone Depletion and CFCs.
Mixed into this atmospheric soup is a highly effective, purely synthetic crisis. You've definitely heard of the ozone hole, but it's vital to know exactly what that means. It's a massive depletion of ozone concentration, specifically up in the stratosphere, with the biggest drop happening right over Antarctica. Normally, stratospheric ozone is our VIP shield. It absorbs harmful ultraviolet radiation from the sun. When it gets depleted, those UV rays just shoot straight down through the troposphere right to the surface.
And the cause? Chlorofluorocarbons, or CFCs for short. Unlike CO2, which is natural, CFCs are purely synthetic products of human activity. Usually, UV rays in the stratosphere are constantly converting oxygen into ozone, keeping our shield strong. But when our CFCs drift up there, they act like a wrench in the gears. They systematically disrupt that oxygen to ozone conversion, destroying the ozone and completely compromising the planet's primary defense against UV radiation. Finally, Section 5, Global Impacts and Action. When the international community looked at all these shifting mechanics, the greenhouse effect cooking things up and CFCs tearing down the ozone, they realized they had to act. Enter the Kyoto Protocol. Proclaimed in 1997, it drew a line in the sand using 1990 as the baseline year for emissions levels. It officially went into effect in 2005 after being ratified by 141 nations. The big ambitious goal? To bind 35 industrialized countries to a strict target. By the year 2012, they needed to reduce their greenhouse gas emissions to 5% less than what they were back in 1990.
The sheer urgency behind treaties like Kyoto isn't just political, it's intensely physical. As atmospheric temperatures rise, we are looking at the melting of massive glaciers and ice caps. On top of that, the ocean water itself physically expands as it warms up, a process called thermal expansion. Combine those, and you get rising sea levels threatening to inundate coastal areas and islands worldwide. And this matters to all of us. We aren't just talking about losing a few empty beaches. We're talking about major global cities and millions of people facing profound social and economic disruption.
Which brings us full circle, right back to where we started, that delicate anchor metric, 14 degrees Celsius. With greenhouse gases throwing a thick thermal blanket over the Earth and capturing that outgoing long-wave radiation, we are literally watching the complex mechanisms push that global average upward.
Leaving us with this final, provocative thought to ponder. We kick things off by mapping Earth's climates using Köppen's incredibly precise 1918 scheme, relying on stable temperatures, precipitation, and vegetation. But if the underlying global temperature and atmospheric chemistry keep fundamentally altering, will the carefully coded climate map we rely on today have to be entirely rewritten a century from now? Thanks for joining me on this explainer, and I'll see you next time.